Hello, my name is Trần Vân Anh from Hanoi University of Mining and Geology, Vietnam. Welcome back to my lesson. Today's lesson is about SAR interferometry. It's called InSAR. The table of contents. In the table of contents, there are four parts. Firstly, I will again repeat about the complex images because it is the core of interferogram. So the next is the interferogram formation. How to create the interferogram from two different singular complex images. So the next is I will introduce about differential SAR interferometry called InSAR. So the next will be the multi-temporal InSAR techniques. Firstly, I will introduce again about SAR data. So SAR data are getting attention due to the importance in real-world application context. A singular complex images, SLC, SAR image can be decomposed into intensity and phase. Imaginary result is this is one position of satellite. It will send the signal to the Earth and receive the backscatter from the Earth to the sensor. It will create one singular complex images. So one complex singular images can be decomposed to intensity and phase. You can see in the first part of this equation is intensity, and the other is phase, is the exponential part up here in this part. So you see in these areas, this is the images for intensity images, and the other is phase images. So a little bit difficult to recognize the thing on the phase, but I gradually explain to you about the phase and you can understand about this. Last time when I talked about the radar theory, I also introduced a little bit about the complex images, but today I also have to talk more clearly about the complex images because it is information that we create the interferogram from complex images. So each pixel provides a complex number that carry amplitude and phase information about the backscatter signal by all objects on the ground surface, like a rock, vegetation, building, and etc., in the corresponding resolution cells. So you see in here, the illustration of the complex number, you see it's divided in two parts, real and imaginary. That means in two directions. So the images, with the images, also one pixel will create one point. One point will also have two parts. That means one part is real and the other is imaginary. But in case of images, they call the real is in phase and the imaginary is quadratures. In physics, I know all of you already studied about amplitude. The amplitude is periodic variable. It measures it changes over a period of time. The amplitude of a periodic signal is a strength relative to the reference value. You see in here, the distance here is shows the amplitude. So here is the wavelength. That means from this to this is the wavelength. So amplitude show the distance from here to here. That means the amplitude of this wave. You also can be heard about the intensity, and from now on you also can be listened many times about intensity. So what is intensity? Intensity equal A square, A that means amplitude square to become intensity. So if the satellite or aircraft in this position sends a signal to the Earth and receive the signal back, that means backscatters from the Earth, it will have the amplitude and phase in 1 pixel of the signal. So one thing you need to know and understand about this, they call it time delay, correspond to the pulse traveling from the radar to A and back again. It calls round transit time. So this is the time transmit and receive the signals. And the other called is amplitude of the echoes. This is distance from here to here. Now I will explain how to compute the phase and amplitude from complex images. The illustration here, you already know about this. This is the complex images divided in 2 parts, real and imaginary, and real called it in phase and imaginary called it quadratures. And A, that means amplitude, equal with square root of I square plus with Q square. So this is the distance from the 0 point to 1 pixel. In here, they call it amplitude, A. And the other is phase. Phase is angle. You see? Phase here. The angle is equal with arctan of Q divide I. So A and phase you can compute can be computed by this equation and this equation. So please remember this one. We will have the exercise to do with the images using 2 equations in here. Now we go to interferogram formation. Last slide you already studied about the one single loop complex images. But in case if you want to create the interferogram, that means you have at least 2 images. So for example, in this, you see in the figures, we have 2 positions of satellite. So if we want to collect the data into different position of satellite but acquire in the same area on the Earth's surface, it will create the interferogram if 2 images acquire in the same area on the Earth. So if we have the first images, for example, first image is U1, so the second image is U2, so we can create the interferogram by multiplication between the first image and the second conjugation of the second images. So it will create some type in like this one. So the first part of the images is the intensity. This one is intensity, and this part is the phase. So here intensity, you see, the image is like a grayscale images. But with the phase images, you can see in here is like a fringes. The fringes vary from blue to red. So each fringe is can compute the elevation or elevation change. You see on the figures illustration in this part, for example, in case of the elevation, the change is there's no change. But in case of the elevation change, that means the have deformation of the elevation, that means have D in this part, it will also exist in the phase. So that's why if we have the interferogram, we can detect the elevation and also elevation change. So here just more explanation of the interferogram. For example, with the first phase, we have phase 1. So with the phase 1, for the first position of satellite to acquire the phase of the 1 point P on the Earth's surface. So with the range, we will have this part of the phase 4 pi divided lambda multiplied with d. In this case, d is distance. And the other is phase scatter. The scattering from this point to the sensor, so called phase scatter. And the other is also with the other position. I mean the second images, second position of satellite is also the same, and create the images with the phase and intensity. So when we want to create the interferogram, we just take the multiplication between the first and the second images. But the second images, we don't take only that images. We have to process the second image to the complex conjugation of that images. That means you see in here U1 multiplied with U2 star. That means the U2 conjugation of these images. So the images now become, the first part is intensity and the second is the interferogram. The interferogram phase, that means in this part, equal with phase 1 minus phase 2. So ultimately, if we have two positions of two satellites and acquire in the same area on the Earth's surface, they have the same frequency and same amplitude, but different phase. It will create the interferogram. And interferogram is very sensitive with elevation and also elevation change. So here, example, you see the phase of the 1 point on the Earth's surface. So in this, you see the ground range, and here is azimuth direction. So two positions of satellite will create the interferogram. So one terminology you need to know is this B. That means the baseline. The baseline of two positions of satellite. They call it the baseline. And also BN. BN is perpendicular baseline. So here the phase equal to 4 pi divided lambda multiply delta R. Delta R, that means R2 minus R1. So we have the interferogram like this one. It's like a fringes. You see the fringes. Each fringe vary from blue color to red color. Now you have just know about the SAR interferometry. But what is the differential SAR interferometry? It's also a little bit the same, but one thing is different. You see, it also have two positions of satellite, S1 and S2. And but in this case, the differential SAR interferometry will have the time span is longer. So when they use differential SAR interferometry, they want to detect the change of elevation. They call it deformation or displacement of 1 point P on the Earth. For example, you see in here the P point in this position. But in the first time, that means the S1 position is acquired data from point P. But in the next time, the position of S2 is acquired the point P, but now the point P is not in this position, is displacement to the other point, maybe in this direction, in the rain direction, the point now become in this point. So this point is have displacement called D. The D is the deformation or displacement, and we want to know exactly what is the displacement and how to compute the displacement from two images. So they call it differential SAR interferometry. So assumption that two images recorded under the same atmospheric condition, they will have the two equations, phase 1 and phase 2, like this one. So if we want to create the interferometry, that before I show you, that means the delta phase, that means phase different between the first and the second. They will take the phase 1 minus phase 2. So phase 1 minus phase 2, in case of phase atmosphere first and phase atmosphere second equal to each other, and phase scatter equal to phase scatter to each other, it will create the equation like this one. That means we remove all this one and this one. So if it is in the very good condition, it will like this one. But in case the reality, it's never happen in like this one, because with the first and the second time, many things change in atmosphere change, and something on the air, maybe it's rain or cloud or something like this. So it's never equal. That means phase atmosphere 1 and phase atmosphere 2 is never equal to each other. And scatter also is because the scatter, in case of the point P now it changed to here, that means scatter 2 will be different with scatter 1. So that's why we want to detect the D, we have to know phase scatter 2 and phase scatter 1. And the difference between phase scatter 2 and phase scatter 1 will detect the D. So in case of difference, we will have the delta phase like this one. After processing, we have this equation. The first part of equation is delta phase flat. They call it flat. That means the delta phase of the point P, but on the ellipsoid P0, they call it delta phase flat because it's on the flat Earth. The second is delta phase of elevation. Elevation, that means the point P is in this position. It have the height from position P to the ellipsoid. That means the height is h. That means here is delta phase elevation. The other is delta phase displacement. That means the point P now is moved to this position, is moved d distance. It will create the delta phase displacement. And the other delta phase atmospheres, that means atmosphere from the first minus the second. So this is delta phase atmosphere, and also delta phase noise, because the first and the second, the noise also different and still exists in this equation. That means the noise and atmospheres. So you see in this equation with the differential SAR interferometry, we had to extract the delta phase displacement. So this one, if we can extract this one, we can detect the displacement from the Earth. So with this one, how can we remove the other thing? So with the other, like delta phase flat, we can remove it because it's easy. It's on the ellipsoid. I will explain after. So the elevation also is not so difficult because of elevation. We can use this elevation model to remove it. And the other very difficult is delta phase atmosphere and delta phase noise. We have to remove this one and to extract delta phase displacement. Alright, so now if you want to remove the first part, that means the flat Earth phase, we have the terminology called is flattening. Flattening is achieved by subtracting the phase contribute of flat Earth. That means the phase on the ellipsoid, we have to remove this. So how to remove this? You see in here is the fringe. The fringe here in this direction is azimuth, and this direction is slant range. So how to remove the flat Earth phase? We use the flat Earth phase equation. We can remove this. We compute and remove this. So here an example. After removing the flat Earth phase, because flat Earth phase is point P on the ellipsoid, it had the equation. So we compute the flat Earth phase, it automatically can be removed. And after removing, the phase now become like this one, the fringes like this one. So here is the mountain. You can see from the foot to the top of the mountain. You see, you can count. You can count the fringes. So if you know the fringes height between this one and this one, this one and this one, we can know the height of this mountain. That's easy, right? So if we want to know the elevation between the first and the second fringe, we can go to next slide. Okay, in the last slide, you see the fringes. After removing the flat Earth face, it had fringes. So each fringes will have the elevation height. So that means the height of between the first and the second fringes, they call it altitude of ambiguity. So altitude of ambiguity will help you to understand how high of the mountain or how high of one object. So in here, we have to compute the altitude of ambiguity so we can know the height of the mountain. You see in here, delta phase equal this part, and in this part they have one thing they call is delta Q. Delta Q is in this. You see in here, in this position of satellite, send the signal to the Earth, and then it goes through this. It will create one point in here, and the height of the fringe will equal to delta Q in here, and absolute delta in this part, and it depends on the theta, that means look angle. So in this equation, how we can extract the delta Q? So from here, delta Q equal with delta equal delta Q divided sine theta. So in case of we compute with Bn, that means B baseline perpendicular equal 100. So it will create delta Q equal 100 meters. So here an example. You see, an example in case of here the equation I copy in here. You see, if delta phase equal 2 pi, that means one fringe equal 2 pi. It will create like this equation, and then we extract the delta Q equal this equation. So the delta Q depend on the Bn. Bn, that means the baseline perpendicular, and the second is lambda, and also depend on the theta, look angles. If we want to extract delta Q, we have to move Bn, baseline perpendicular, to denominator, to here. That means if we want to compute the delta Q, Bn is long, that means this one is small. So that's why the delta Q usually depend much more to the baseline. It's a long baseline, the delta Q is small. If shorter baseline, the delta Q is large. Here an example. For example, with the BN equals 50 meters, the delta Q is approximately 188 meters. So for example, from this foot of mountain, you count in here 1, 2, 3, 4, 5, and 6 will multiply with 188 meters. The other, if the BN is 250 meters, delta Q now equals 37 meters. You see 37 meters you have to count from here to the mountain. So just very rough if you count the fringes from foot to the top, but actually it automatically compute the height of the mountain for you. So in this case, it's very detailed if the delta Q is small. If the delta Q is larger, it's not detailed. Maybe something is be ignored in some here and some here. So it's better to take the BN is larger. But usually it has limitations, so we'll discuss about the limitation. So remember about the greater the baseline, the greater the high accuracy. One component that I already mentioned before in the equation of differential SAR interferometry is atmospheric phase. So atmospheric phase is the thing that we need to remove it. So what is the atmospheric phase? This is the phase due to atmospheric artifact does not depend on the baseline. Before I also said about the flat earth phase. So flat earth phase is the other thing that we can remove and create the phase without the flat earth phase. But in this case, the atmospheric phase does not depend on the baseline. That means the distance between the first and the second. And it also sensitive with the phase to the atmosphere is related to the wavelength. The longer wavelengths are less sensitive to the atmospheric distortion. For example, the radar wavelength, there are some different types like a C-band, X-band, L-band. With C-band 5.6 centimeters, L-band is 23 centimeters, but X is only 3 centimeters. But in case of L-band, it can penetrate deeper, so it's less sensitive to the atmospheric than the X-band. So a propagation delayed usually about 2 centimeters would result in the additional phase of almost full fringe at C-band, but it's only 1/6 of the fringe at L-band. That means with C-band, it had much atmospheric phase existed on the phase, the total phase. So that's why in the areas like Southeast Asia, there are cloud and fog and something inside the atmosphere. It usually have the atmospheric phase existed inside the total phase. So that's why we need something to remove this. So I will explain more in the other lesson to how to remove the atmospheric phase. One terminology's name is complex coherence. That means you need to care. So when you have the pair of images for creating the interferogram, so with the two images, the correlation between the first and the second images, they call it the coherence. But with the single look complex images, with the second complex images also, it creates the complex coherence. So what is the coherence? It measures interferogram quality. That means when we see with the coherence value, we know about the quality of the pair of images. So how to compute the complex coherence? For example, if we have two co-register complex SAR images, U1 and U2, and one calculate the interferometric with two images, the coherent gamma as a ratio between the coherent and incoherent summation. You see in here the equation gamma equal with the first images and the second images sigma, and divided to the square root of the absolute U1 square and U2 square. Notice that the observed coherence will range usually from 0 to 1. When coherence is close to 0, total decorrelation has occurred. So when it's close to 1, indicate a very stable and strong scalar objects. So coherence is a measure of phase noise of fringe visible. So if we have to create the interferogram, usually we have to check the coherence and decide it will be better to use that interferogram or not. Here an example of creating the coherent and interferometric phase. You see on the left hand is the coherence. So 0, that means the blue color, and 1, that means the purple color. So in this area is high coherence, is nearly 1 or less than 1 in this area and this area also. But in here, maybe in valley is have blue color. That means very low coherence comparing to the interferometric phase in this area. So the phase here, it continuously look very smooth. But in here, in this area, low coherence, the phase is not so good and is not easy to recognize in this area. And this area also, you see in this area, you cannot recognize the fringe in this area. But in here, you can see the fringe. And in here, maybe it is the urban area. You see the pattern in here, you can recognize it is the urban area. So urban area, as I explained before when you study about the radar theory, in the urban areas have the corner reflection. With corner reflection is have very high sensitivity with the signal. So usually it create very bright pixel, and it also create very high coherence between the two pair of images. You already understand about the quality of the pair of images, coherence, and also how to create the interferogram. But in this slide, I will introduce you about the critical baseline. It's one thing you need to remember, because with the critical baseline, it helps you to select the baseline, the good baseline for DM generation. So what is critical baseline? In geometric decorrelation, it's really on the side angle difference of the two subscenes of the interferogram. The critical value of the baseline at which complete decorrelation occurs is given by this equation. You see in this equation, the name BC, that means baseline criticals. Lambda is wavelength, R is the slant range, and theta is look angles. So for example, in case of C-band, the critical baseline is about 1100, with R is 850 kilometers, with theta is 23 degrees and lambda is 5.6 centimeters. With A-load pulsar L-band, the critical baseline is about 4 kilometers, with R is about 730 kilometers and theta is about 35 degrees and lambda is about 23 centimeters. Continue with accuracy of interferometric production. What is the accuracy of interferometric? The code is standard deviation phase. So phase coherence can also be used to estimate the expected phase noise. Hence, the expected accuracy of the interferometric production can compute in this equation. Sigma phase equal with square root of 1 minus gamma square divided to gamma and square root of 2n. So gamma is a coherent. Usually it's less than 1. It varies from 0 to 1. That I already introduced to you. And n is number of look. Maybe you still remember the number of look. That means many times the position of satellite is looked to one point on the Earth. So the corresponding number of look is applied for the synthetic aperture radar. It create the synthesized large antenna. Remember? So number of looks. So you see in here, if you want the sigma phase is small, so n need larger, n larger and gamma larger, that one will be reduced, right? I have just talked about the creation of interferogram for one pair of images. One pair of images, that means there's only two images acquired in different time, the first and the second. But in that case, there are something we cannot remove. That means these atmospheric phase is very, very difficult to remove the atmospheric phase in case of only one pair of images. So that's why they are create another method called multi-temporal InSAR technique. So what is multi-temporal InSAR technique? That means we use many images, time series of images. It's not only two images, but many images. So they divided in two main categories of methods. They call it distributed scatter DS. The typical of this method, they call it the S-bus method. That means small baseline subset. All scattered within the resolution cell. You can see in here, this is the S-bus method. It creates the baseline, it's like here, right? So the other method, they call it point scatter, PS. And also they have the name persistent scatter. Persistent scatter, PS, InSAR. So they create one main point or master point, master images, and the other is slave images. Create the baseline like a star, like this one. Yeah. So two types of multi-temporal InSAR technique using many images. So with a single master, for example, in case of from this point to this point will create one baseline. So maybe in here there are many baseline, create many baseline like this one, for detecting some change on the elevation or deformation or displacement of the object on the Earth. And in this one, you see the baseline create like this one. Sometimes it create like a triangle. So you see in here maybe 100 images. There are many. So the processing is very heavy with using many images. So in here is more explain about the multi-temporal InSAR techniques. A number of advanced InSAR techniques have been developed since 20 years ago with PS and SAR from polymer, SBAS, that means small baseline subset from CNR IREA. So another IPTA from gamma remote sensing. The other is PSP from EJOS and STAM and PS from Stanford University, and many other. They are usually named as PSI technique, persistent scalar interferometry. So that's all for today. Here's a reference. I use some reference. You can access this reference to check some information like the ESA website, Alaska Satellite Facility. In this website also you can download the images and many things. You can read in here very useful information. Thank you for your listening. Thank you and see you next time.